guess we'll have a short, like maybe 10 minutes open problem session related to the last couple of lectures. So, I mean, I'll mention a couple of problems and then open it up for anybody else who has comments or ideas about problems. So, okay, so the most obvious open problem, I mean, it's been a theme in the last 3 lectures, including Jan's lecture, is that all these proofs prove that certain objects exist, but we don't have algorithms for finding them. So we have a bunch of algorithmic questions. So one is there an algorithm for Weaver's problem? This problem of given a set of vectors, can you partition it into 2 subsets? Says that for each subset, the norm is much less than the norm of the original covariance matrix. I mean, this has several interesting combinatorial problems as subcases, which I didn't talk about. But I mean, part of the reason people were interested in this conjecture is that if you apply it to Laplacians of graphs, you get fairly interesting statements about graphs. So here's an easier problem. This is something that's called a spectrally thin tree. So a spectrally thin tree is a spanning tree of a graph. And let's suppose the well, or actually, yeah. So and let's suppose the graph G has m edges. Now, a spectrally thin tree is a tree which approximates the graph in a particular sense. The sense is that if you look at the Laplacian of the graph and you look at its quadratic form, then this is approximated by the Laplacian of the tree in the following sense. So certainly the okay, so the Laplacian of the tree is certainly at most the Laplacian of the graph because it's the tree is a subgraph of the graph. And the Laplacian of the tree is also I mean, it has one eigenvalue equal to 0 because it's a Laplacian, but it's connected, so it has otherwise non-zero eigenvalues. A spectrally thin tree is a tree with the property that the tree, not only is it smaller than the graph, it's smaller than the graph in about the appropriate ratio. So the tree has n-1 edges, the graph has m edges. A spectrally thin tree is a tree such that the Laplacian of the tree is at most some constant times n over m times the Laplacian of the graph. So you want to think of this as a tree which is proportionally smaller than the graph.
M
is the number of edges in the graph. N is the number of vertices.
M is the number of vertices.
N vertices. So really this n is an n-1. This is the ratio of the number of edges in the tree to the number of edges in the graph. And this is some constant. So why are people interested in this statement? Well, in particular, one thing this implies is that if you look at any cut, so if you look at any, if you look at the boundary of any set in the tree, if you look at the number of edges leaving this set, this is at most, again, C n over m times the boundary of the same set in the graph. So this implies a statement about all cuts by plugging in just 0, 1 vectors in this quadratic form. Okay, so not all graphs have these spectrally thin trees, but one implication of Weaver's conjecture, one thing that it implies is that every graph has a spectrally, or maybe I'll, every graph has a tree with the Laplacian of the tree bounded by R times the Laplacian of the graph, where R is the maximum effective resistance of an edge in the graph. Okay, so it's quite natural to see why something like effective resistance should show up, because the canonical graph which doesn't have a thin tree is this graph, right? So this is a graph. But any tree is going to completely saturate this cut, right? It's not going to shrink that cut by a factor of n over m. And that edge has effective resistance 1. So this is one way of articulating, saying that a graph doesn't have these kind of edges. And so we know this is true. Okay, this is a simple consequence of Weaver's conjecture, which you can prove. And so maybe a simpler question, a combinatorial question, is can you get an algorithm for spectrally thin trees? There's also something called just a thin tree, a combinatorially thin tree. And one reason this is relevant, so I'll just make a remark, is that a combinatorial thin tree and that just means this inequality holds only for 0, 1 vectors. So only for cuts is known to exist with, instead of the maximum effective resistance, you have R equal to some polylog log n divided by the edge connectivity. This is due to Anari and Oves-Karan. This has implications for the asymmetric traveling salesman problem. This is why they were interested in this. And again, this does not have a constructive proof. So we have all these nice combinatorial statements about graphs. We know that these trees exist, but we have no idea how to find them. Maybe this is easier than solving Weaver's problem in full generality. A third, perhaps easier algorithmic problem is, or something that's suggested by what happens for the matching polynomial is there an algorithm for approximating the roots of mixed characteristic polynomials? If you could do this sufficiently well, then you would get a solution of Weaver's problem, because all these interlacing techniques, all you need to do is approximate roots of mixed characteristic polynomials very well. So this is another sort of more analytic question.
It's the largest root, right?
I'm sorry, largest root. And maybe a sub-question here is, do the moments of the roots count anything? So this is very speculative, because it's inspired by the fact that for the matching polynomial, you get tree-like walks.
But the fact that they count tree-like walks doesn't help much algorithmically, is it right?
It doesn't help much algorithmically, but it yet again provides maybe a line of attack, right? If it counts something, maybe you can count it using Markov chains.
But so far we don't quite know how.
So far we don't know how to count tree-like walks either. So maybe the easiest question is count tree-like walks. Count tree-like walks up to 1 plus epsilon accuracy in time polynomial in n and 1 over epsilon. So right now we have this in time exponential in 1 over epsilon. If you could count tree-like walks, maybe that's a stepping stone to eventually doing this, which would imply all this other stuff.
That could be easier.
What could be easier? Counting tree-like walks?
No, the moments of the because.
Oh, this?
Yeah, because you have some, I mean, for the graphs, you have some specific vectors. It could be, I mean, it doesn't have to do anything with tree-like blocks. We don't know which one is easier.
We don't know which one is easier, meaning?
Computing the moments of the mixed characteristic polynomials when the vectors come from the graph.
Yeah. Okay. Yeah.
Easier than counting tree-like blocks.
Is that the same or? Oh, okay.
You're saying when the vectors come from, you're saying in these applications, the vectors come from a graph, which is not actually the same as what you do for the matching polynomial. Yeah, so you could consider various subcases, right? So subcases of this are, I haven't told you what the reduction to these thin tree problems is, but you get a special class of matrices when you do that related to Laplacians of graphs. Maybe you can do it for that subcase. Yeah, so these are some of the algorithmic problems, and I guess maybe I'll just leave some time for people to say their own problems. Otherwise I can say more, but.
I have a question. So this thing, using this matrix sum of bounds, so there are algorithms when this delta is 1 by log n.
Yeah.
Can you improve it to maybe 1 by root log n or something?
Yeah, that's a good question. So yeah, what Mohan is saying is there's an intermediate regime, which is Weaver's problem is easy for delta equals 1 over log n just by picking random signs. Can you even solve it for just any delta that's bigger than this?
Could we get log n over log n by Harvey algorithm?
I don't think you get log n over log n. I mean, in that example, you get log n over log n. In the balls and bins example, you get log n over log n. I don't think matrix turnoff gives you log n or log.
No, Harvey always resolve the. So.
Oh, okay, fine. Okay, fine. So let's make this log n. So okay, yeah, there's a result of Harvey and Olver, which gets log n over log n, right? Is that right? Yeah. Okay, thanks. So I mean, okay, there's this, as you can see, that there's this hardest problem, and then there are various subcases that are interesting and possibly easier. So maybe it's worth attacking one of the combinatorial formulations first. Any other comments? I mean, okay, one other obvious open problem left open from the last 3 lectures is, can you construct non-bipartite Ramanujan graphs? So in these lectures, we explained how to construct graphs whose second eigenvalue is bounded by 2 square root d minus 1. That didn't actually use anything about non-bipartiteness. But if a graph is about bipartiteness, but if a graph is bipartite, its eigenvalues are symmetric about 0. So if, for free, if the graph is bipartite, you get that lambda n minus 1 is at least minus 2 square root d minus 1, which is the definition of a bipartite Ramanujan graph. But there's this weird gap, which is we know how to prove all this stuff using this trick, controlling just the largest root, because remember, interlacing only allows you to control one root at a time. And we know how to use this sort of rather cheap trick to just say, oh, well, you get one side, you get the other side for free because it's bipartite. But we actually don't have any techniques for controlling 2 roots at a time. So the question of can you construct graphs for which all the non-trivial eigenvalues are bounded in absolute value by 2 root d minus 1 is still open, only known for prime powers plus 1.
So for Ramanujan graphs, the Lubotsky-Phillips-Sarnak constructions are Cayley graph.
They're Cayley graphs, yes.
Is there some way of using this method to give something that has more symmetric?
Yeah, that's a great question. So maybe I'll write it. I don't know where I'll write it. Maybe I'll write it over here. So one more question is, can you get Ramanujan Cayley graphs? using whatever method, but perhaps using interlacing families. Right? So Lubotsky-Phillips-Sarnak proved certain Cayley graphs are Ramanujan graphs. This has very good computational properties. Cayley graphs are strongly explicit. That means that for any vertex, you can figure out what its neighbors are in polylog time. So that's still open. Can you get strongly explicit expander graphs for all degrees and maybe even all sizes? We don't know. So right now, again, these techniques are highly non-constructive. We don't know almost anything about the graphs that they produce.
So I have a question. So all of these are for regular graphs. For irregular graphs, by looking at the universal cover, you can also define some kind of spectral radius.
Yes.
Is there some?
Yeah. So that's a good question. So everything I said works for that also. So for any graph.
So what is the setting?
So the setting is you take any graph, you look at its universal cover. It has some spectral radius. You can prove that the roots of the matching polynomial are bounded by that spectral radius. So by what I discussed yesterday, that implies that every graph has a cover whose roots, new eigenvalues, are bounded by the spectral radius of the universal cover.
Okay.
So irregularity is not a problem. Any other? Okay, well, I guess we'll just end here.